Hello, everyone. My name is Nathan Peck. I'm a developer advocate for Elastic Container Service at AWS. And today, I'm pleased to be here to present a Getting Started guide to Docker and Amazon ECS. So the goal of the session is we're going to be going over some of the basics of how to use Docker, what is Docker, why would I want to use it, and then a brief overview of what ECS is and what the components of it are. And then I'm going to be joined by Jean Dominguez from Realtor.com. And he's going to talk about the story of how Realtor.com was able to start out using ECS and the lessons that they learned along the way. So to start with, let's discuss an introduction to what a container is and what Docker is. Many of you here have probably created many applications before, and you're familiar with the different pieces that go into creating an application. Typically, if you're running an interpreted language, you're going to need a runtime engine. You have your actual application code. You have any dependencies. For example, if you're using Node.js, maybe you're using npm install. For Python, maybe you're using pip. But you have a variety of different dependencies that you need to install for your code to run. And then you're going to have your configuration, which are the values, maybe environment variables, maybe values about how much CPU or memory are required. And you're going to be using those alongside your code as well. And as a whole, these four components function as your application. But in running your application, there are a variety of different environments in which you need to run it. So for the local developer, maybe they're developing on their laptop, and we also have a staging or a QA environment where code is placed temporarily while we test it to make sure that it works. Maybe there's a production environment, maybe there's even an on-premise environment. With all four of these environments, one problem that often arises is that there's configuration drift or dependency drift or runtime drift across those four different environments. So here's an example of an application which is being developed on a local laptop. The developer is running version 6.0.0 of Node.js, and their code runs fantastically. They push it to the staging environment, and on the staging environment, when that environment was set up, it was installed with Node 7.0.0. The code still runs, but then when that code gets promoted to production, there's a machine on that production cluster that's been around for a while longer, and it's actually running Node 4.0, and everything breaks. And so this leads to this question of, why did it work on my machine, but it didn't work in production? And when you encounter an issue like this, it's very disconcerting because it causes you to lose trust in your deployment lifecycle and whether or not you'll actually be able to deliver an application to your customers. So the solution that's been created to help solve this problem is Docker. So the purpose of Docker is to allow you to take your runtime engine, take your dependencies, and take your code, and package them up into a consistent unit of deployment. And this artifact that you create as part of your build process is something you can deliver to any machine. It's something you can run locally, and you'll be confident that it's going to run correctly because it's going to bring along with it the proper runtime engine, the proper dependencies, and the proper code. The way a Docker image works is it's built on a series of layers. And those layers each correspond to a command that's part of your build process. So this is a diagram that shows an example of how a container might work. We start out with a kernel. And on top of that kernel, we add a base image, which is adding the system libraries and dependencies of Ubuntu. Because we want to develop an environment that's using Node.js and Nginx, we add two layers to that image, which correspond to the Node.js binary and the Nginx binary. And then we have a writable layer, which we're going to add our application code to. And the finished container image is the sum of all of these different things we've added to it. It's kind of like working with a Git repository. You commit some code, you add some more code, commit it, add some more code, commit it. And the final project is the sum of all of those commits once they're added together. In a similar way, the container image is the sum of all the layers that you've added to that image. And when you have this image, it allows you to have really easy reproducible builds. You can rerun these commands at any time to regenerate these layers. And when you take this image, it's immutable. It serves as a template that you use to launch a container. And any container that you launch, it has this top writable layer. But when you are done running that container and you shut it down, any changes that you've made no longer persist. The reason why this is important is if you think about the old days, perhaps when we used to deploy applications to servers, and we would do it via FTP, perhaps on some virtual host somewhere. maybe using SCP if you're a little bit more advanced and had SSH access. At that time, with those types of deploys, what would often happen is you would have to run a command to copy your code in, run a command to install a dependency, and if something failed along the way, if you actually went to go execute that application version you had deployed, and something was wrong, you would need to do a rollback and try to get things back to the state that they were in before you did this deploy. And it was often very hard to do so. Once you've installed a new version of a binary, now you need to hunt down and try to figure out how to get the previous version of that binary. And what could be even worse is, if the application had failed badly enough, it could have mutated the machine in such a way that your application would just no longer run on that machine. And you would have to start over from scratch and try to provision a machine or try to rescue that machine in some way. So Docker containers changed the game by having this immutable container image, which when you launch it, it's ephemeral, you can run it, you can stop running it, discard it, and run a different one. And the base machine is just an empty shell that stays the same underneath the hood. And so this gives you this reliability. When I actually go and deploy the Docker image, it runs the exact same way on my local laptop. It runs the same on QA. It runs the same in production. And it runs the same in my on-premise environment. And so I have this confidence that the application I developed on my local laptop that worked there is going to work everywhere that I run it. Now, at this point, it's important to consider the difference between a virtual machine versus a Docker container. If you've been working within the AWS ecosystem, you probably use EC2. You're familiar with the concept of an Amazon machine image and AMI. And so you may think, well, the benefits of the Docker sound very similar to the benefits of a virtual machine, such as an AMI. There is a difference, though, and that's that an AMI is very heavyweight. Due to the way it runs, there's a lot more overhead associated with that. Generating an AMI takes more time. It's going to be much larger, oftentimes in the order of gigabytes in size. Versus a Docker image, due to the way it's designed, can often be in the range of 50 to 70 megabytes because it's just containing your application binaries and the bare minimum required to execute those alongside your dependencies. And so what this allows you to do is you can actually run multiple containers within a single instance, and you can run a lot more of them than you would be able to run virtual machines within an instance. If you're using a VM provider, you're probably only going to be able to run a few different VMs on a particular instance before you run out of resources and you start to have issues. With containers, it's so lightweight that it's almost just like running another process. And so you can run 10, 15, 20 containers easily on a mid-sized instance. And what this means is that you go from a state where you are barely utilizing your instances to being able to densely pack them with applications and fully utilize that instance. So to summarize the benefits of the container in Docker, it gives you this portable application artifact that runs reliably everywhere that you want it to run. So it gives you confidence you'll be able to repeat the build and know that that code you developed is actually going to run in production. It allows you to run multiple different applications on the same machine, or even multiple versions of the exact same application on the same machine in such a way that they don't conflict with each other. So this is huge if you're doing something like upgrading the version of your runtime, and you're moving from Node.js 6.0 to Node.js 7.0. You can actually run two containers in parallel, and one has Node.js 6.0 inside of it in your application code, and the other has Node.js 7.0 inside of it in your application code. They're running in parallel. They're not conflicting with each other because they're not sharing the root base file system. And then finally, the benefit is you get better resource utilization by packing an instance with multiple containers in order to fully utilize the CPU and memory resources of that machine. And that gives you savings. So from here, it's time to introduce Elastic Container Service and explain how it integrates with Docker and the reason why you would use Elastic Container Service. So when it comes to Docker, running a single host is easy. If I'm working on my local machine, I have a Docker command line app on my machine. I type Docker run and the name of my container, and that Docker container starts up. I can type Docker PS to list all the Docker containers running on my machine, and I can see a list. And so it's easy to launch containers. It's easy to manage them. It's easy to check the stats on those containers on a single host. But running a single host isn't what you want to do on AWS. People use AWS because they want to run a variety of hosts. They want to run a really large cluster of hosts. And we have very large customers that are using Elastic Container Service to solve this problem of how do I distribute my containers across gigantic clusters. So for example, Mapbox has shared that they run on 3,500 instances at peak. And we have a customer, Mobfox, that serves over 1 billion requests an hour using a fleet of 1,200 instances. The way they do this is by using Amazon Elastic Container Service. So this diagram shows the basic components that go into Amazon Elastic Container Service and how they work together. And I'm going to zoom in on each one and highlight each one and explain what it is. So to start with, we have a cluster of hosts running in Amazon EC2. And if you've watched the keynote this morning, you'll know that there are now 2 different ways that you can run a cluster of hosts. You can run them directly yourself if you want to customize, for example, an AMI, and you want to run a fleet of Ubuntu machines with a specific customization, or you can use Amazon Fargate, which is a new solution for running a container in a serverless manner. You can just give a container to Amazon and say, I would like to run this container somewhere, and Amazon will provision a machine for you behind the scenes without your intervention. But at the lowest level, somewhere you need a machine to run your container. And whether you're managing that machine yourself or if you're using Amazon Fargate, there's still a machine there. So on that machine, there's an ECS agent. This agent is what controls what happens on that machine on your behalf. So you think about it, if you wanted to control the machine yourself, you would SSH in, you would run a command on it. But you don't want to do that manually. So the ECS agent acts on your behalf. It's consistently running on that machine, and when you want to do something, it does it on your behalf to launch a container, restart a container, stop a container, fetch stats from a container. Whatever you need to do, it will do it on your behalf without you needing to manually go into the machine and do it. And at the top level, there's an API, which is what you use to interact with the cluster as a whole. And you can give really high-level commands to this API. So for example, I can say, I want to run 4 copies of this particular application container distributed across 3 availability zones, and I want to run them on instances that have the particular type T2.star. And so Amazon ECS will take that high-level command. It will check the state of the cluster that you have provisioned, and it will find ways to place those tasks onto instances to fulfill the command that you gave to it. And because it integrates really well with the rest of the ecosystem, you can also give it commands like, I want to run this container with a particular IAM role, and I want to run this other container with another IAM role. And so this allows you to give different containers access to different resources on your AWS account. So I could talk all day about the API and its features, but the thing to take away is that it's a high-level API where you give it a sensible command about how you want to run the application, and it communicates with the agent and instructs the agent what to do on your behalf. The container task is ultimately what ends up getting placed on the instance when you ask it to run a container. And the task is basically one step above the container. The container is your application. The task is your application plus the configuration about how you want to run your application. So for example, what environment variables does your application need to operate? Does it need disk access? Does it have a port that it receives traffic on? Does it have any particular limits for reading and writing files that need to be set? So the task is where you set all of these things about your application container, and ECS will communicate with the ECS agent and place that task onto a machine. And then the final piece of the puzzle that I want to talk about is the load balancer. And this is how you get traffic to your containers. So you can run a container which is just running a job to completion and then exiting. But the more interesting scenario is you're actually running a service that you want to keep running persistently, and it's receiving web traffic. And so with a load balancer, Amazon Elastic Container Service will actually configure the load balancer on your behalf, as well as place the tasks onto instances in your cluster. And there's a one-to-one parity between those two things. So when Amazon ECS places a task onto a machine, it will also reconfigure the load balancer to direct traffic to that task. And so this makes it very easy for you to just give that command to the API and then trust that traffic will eventually reach that container without needing to go in and do any manual intervention or configuration of how the traffic gets there. So after this brief overview of the basic fundamental concepts of ECS, I want to highlight that ECS is designed for many use cases. So you can use it for a long-running application by asking Amazon ECS to keep, for example, 3 copies of this application running at all times. And so if one of them crashes, it will restart. If a machine is taken out of your cluster that was hosting a copy of your application, it will replace that copy that was lost with a copy of the application that's running on a different machine. You can also use ECS for one-time jobs. You say, I want to run this particular batch job or this particular ETL job to extract some data from a database. I want to run it one time somewhere in the cluster, and I don't really care where it runs as long as it runs. You can also run multiple different schedulers inside of your cluster. So you can have a scheduler which is running a job once a day, once a minute. You can have a job which is running every Friday at 4 o'clock. And you can have those running alongside schedulers which are doing things like keeping an application running persistently. The overall cluster has all these different commands that you've given the API, and it's finding ways to run all the things that you've asked it to run efficiently and simultaneously. Amazon Elastic Container Service is also designed for use with other AWS services. So it integrates really well with Elastic Load Balancing, Elastic Block Store for storing data, virtual private cloud. So this allows you to separate out your containers and prevent them from being accessible by attackers. CloudWatch, all the metrics for CPU and memory and your logs from your containers are all going into CloudWatch so that you can have full visibility into what's going on in your cluster. It integrates really well with identity and access management. So this allows you to give different processes that are running on the same machine access to different resources so that your password service, for example, can access a DynamoDB table that's storing your passwords, but then your other service is only accessing an S3 bucket. And the 2 different containers that are running on a machine will only have access to the specific resources they require and not global overarching access to everything on your account. And then finally, it's also integrated with Amazon AWS CloudTrail. So you have this audible log of everything that's happening in your cluster and actions that people have taken to launch things or run things in your cluster. And Elastic Container Service is designed for massive scale. So by fully managing the control plane on our side, we're able to seamlessly scale up to thousands of hosts and really hundreds of thousands or even millions of tasks across your cluster. And even at that scale, you still have this control, fine-grained control and monitoring of everything that's happening inside of that cluster. So now that I've briefly introduced Docker, I briefly introduced Elastic Container Service, I want to bring up Jean Dominguez from Realtor.com, and he's going to be telling us the story of how Realtor.com came to use Elastic Container Service and lessons they learned along the way.
So, thank you, Nathan, for that awesome introduction to ECS and containers. My name is Jean Dominguez. I'm Director of Cloud Services for Realtor.com. Excited to be here today to talk to you about our transformational journey and how containers and ECS specifically played a significant role for us. Realtor.com is part of a family of products that are designed to make all things home simple, efficient, and enjoyable. We offer the most comprehensive source of for-sale data among all the competing national sites, as well as information, tools, and professional expertise to help people move confidently through every step of their home journey. We are also a key part of News Corp, which has given us great opportunities to collaborate with other News Corp business units, including Dow Jones, News Australia, News UK, and the Real Estate Australia Group. And of course, we're part of the largest global digital real estate network. So, Realtor.com pioneered digital real estate 20 years ago. It's not unusual for a company that reaches that level of maturity to have a great deal of technical debt as well as legacy systems. and those can dramatically affect your product velocity. So in 2015, we started a program to transform our technology organization, and not just from the standpoint of our technology stack and the product itself, but everything about how we produce, deliver, and support our products. And at the center of all of that, we put the customer first. We require that we now get feedback from the customer and iterate on that feedback to improve the product velocity and quality. We also decided at that time to essentially rewrite all of our core products from the ground up. We weren't going to take anything from those legacy systems and try to port it over. Everything would be built as if it were a greenfield project. And we would use DevOps, Agile, and Cloud as our people, process, and technology model. We began to evangelize the idea of keeping it simple. We had a tendency to build very complex application patterns and very complex systems architectures. And that led to those monolithic applications. So rather than thinking about, I'm building an application, we started to tell people, you're building a service. It wasn't necessarily from day one, microservices are the hot thing, but we definitely wanted people to provide APIs to other business units and be service oriented, which ultimately did lead to microservice architectures. We also wanted to be cloud first. When we were acquired by News Corp, they had a goal of being 75% in the cloud. We said, why stop there? We'll just go 100% in the cloud. And we chose Amazon as our cloud provider. As long as we were in Amazon, we thought, why not utilize all the Amazon platforms? We didn't feel that there was as much lock-in as people are afraid of, because I still own my code, and I can still deliver my code wherever I want to deliver my code to. So we wanted to utilize the Amazon platforms and, of course, build immutable infrastructure, because we had seen over the years quite a bit of that drift that occurs in the data center. Now, our initial deployments into the cloud did not use containers at all. We used a build-burn, also called a bakery model, where you essentially start with a base AMI that can be either provided by Amazon or by an operational team. You build an instance out with your runtime, your code, your dependencies, maybe some of your configuration as well. You take that, you burn a new AMI, and that AMI becomes your artifact that you're going to deliver across multiple environments. It's very simple to deliver those AMIs by updating launch configs and scaling groups, then spin up instances, you throw an EOB or an AOB in front of it, and everything works great. Why would you want to do anything else? Well, as we pointed out earlier, there are some problems with just building and burning AMIs. One of the largest ones is that it creates large artifacts, very large artifacts. And 90% of that artifact is the same from one service to the next. A single team will start grinding out AMIs multiple times a day. It's not long before you have thousands of AMIs across multiple accounts, and you're trying to manage the versioning of all these AMIs. You're not quite sure what's inside that AMI. Did they build it from my base AMI? Did they build it from someone else's base AMI? Do we now have drift in the AMI itself? All of this was just a nightmare around management. And the truth was that AMIs only needed to be built once or twice a month. When Amazon makes a change or when we found it necessary to make a change to the AMI. So the obvious solution was to move to containers. Now, this was two and a half years ago. But we saw the benefits of using smaller artifacts, smaller by orders of magnitude. There's less duplication from one service to the next. Some people argue that there's still quite a bit of duplication because your runtime engine, your libraries, and et cetera may be the same, but it's very small. There's plenty of artifact repositories that can help with the management of the Docker images. You can use ECR, you can use Docker Registry, you can use Artifactory. And with the smaller artifact, as well as the fact that your cluster may already be running, it is much faster to do those deployments because you're only launching the task. You also get better portability. You can't move AMIs outside Amazon without rebuilding them. And you can also use the Docker containers on local machines as well. And there's a potential for cost savings through better resource management. I'll explain that a little bit more in a minute. So we spent a lot of time talking about the containers. We've talked about ECS a little bit. But what happens when you have a large organization, 500 developers, 50 teams, 4 different locations, 5 different VPs working on dozens of products, you get very different business needs and opinions about what the right choice of your orchestration layer for container management is. We basically had 3 camps. One wanted to use Kubernetes, another wanted to use Docker Swarm, that was a couple years ago, and the third wanted to use ECS. Most of the teams that wanted to manage their own were very mature DevOps teams who knew everything about Amazon and would have no problem managing it themselves. The teams that were onboarding, though, wanted to use containers, had no interest in managing the orchestration layer, and so they wanted to go with ECS. Cloud Services took the point of view of, we are here to enable development teams to produce and deliver their product. We don't want to get in the way, and we're not really sure which one is the best answer. It may be that they all are. So we kind of let it go out as a bit of a bake-off to see which one would gain traction. So the first phase with containers on ECS was actually using Elastic Beanstalk. So if you're not familiar with Beanstalk, it is an orchestration platform provided by Amazon Web Services as a platform as a service. And it adds an additional layer of abstraction to simplify the deployment of code and creation of resources. It was traditionally used for actually creating a source package that you would just give to Beanstalk, and it would launch your front-end web applications and that sort of thing. But it now supports Docker images, and it can manage the ECS task definitions, scaling groups, CLBs, ALBs, and everything else that is required in that stack. You only need to provide 3 artifacts. One is the AMI. Again, it can be an Amazon AMI or one that you've built yourself. Your Docker image, of course, and then your application configuration is provided either through the Elastic Beanstalk CLI or through the Elastic Beanstalk console. And the cool thing with the Beanstalk console is that it is a single pane of glass. It is one place to go to configure the entire stack. You don't have to jump between different areas, looking at EC2, looking at CloudWatch, looking at ECS. So that pattern took off like wildfire. It was easy to use, very low learning curve. Most of the teams were already familiar in some way with Beanstalk. And the cool thing was that the teams now started to share their delivery patterns across those organizational lines. Now we've got teams of developers actually talking to each other, solving a common problem. Issues were that their deployments were still slow. And I have slow in quotes because an amazing thing happens to a developer when they move from on-prem to the cloud. Slow used to be 24 hours, now slow is 10 minutes. So we still wanted to improve the speed a bit. The problem was that for each new task, at least Elastic Beanstalk launches a new instance. You can run multiple tasks per instance, but if you've configured it that way and you need one more task, it's going to launch 2 more tasks on one instance. And it offers very little in the way of managing that application density. So for those reasons, we were running too many systems, and we wanted to improve, or rather, we weren't meeting the requirements of faster deployments and lower cost. So then Cloud Services gets involved and works with several teams who reached out to us and wanted to move away from Beanstalk. They weren't sure how, so we started by helping them out with the new artifact, which is a CloudFormation template. So rather than using Beanstalk to orchestrate, we now use CloudFormation to orchestrate. You still have to have your Docker image and your base AMI, but the difference now is that you're going to describe everything in the stack. You've got to have a more complete understanding of all of the elements and primitives that are required. But the cool thing then is that you now get much finer control over your application and task placement by using CloudWatch. And you can now not only capture the Amazon platform telemetry, but you can also capture your application telemetry in CloudWatch and create custom metrics to then either create CloudWatch alarms or CloudWatch events, which they can then trigger AWS Lambda functions to directly manipulate either ECS or the auto-scaling groups. So today, we're now moving towards standardization. We have working patterns. We have wide adoption of ECS. So today, all new containerized applications are going to be delivered using ECS as the orchestration layer. We have a guild that is focused on the standard delivery pipeline for containerized applications using ECS. That guild is comprised of technical leaders and developers from across the entire organization, every location, every product team. If they're using containers, they have representation here. And we continue to evolve and improve our utilization of the platform and then share those improvements back to the rest of the organization. One of the most recent things we had the opportunity to do was actually play with the new Fargate product. It works as advertised, and we were able to share that internally with other teams. I think the biggest question was, does Fargate invalidate all the things we had done before? And the answer is no, it doesn't. It has its use cases. It is still early. It will continue to evolve, and we will continue to evolve with it. And that's the message that I have for today, is evolve. Don't try to build a perfect platform or process on day one. You'll get to day 300 and realize you still don't have the perfect platform or process. You're better off just getting started and taking sort of a minimum viable product or a minimum viable process approach, and then iterating on that. Elastic Beanstalk is a great way to get started. You can still do that today. I think the key is to communicate, get feedback on the process. Is the process working? Is the process working for your customer? If you're in operations, your customer is a developer, so you want to get their feedback. If you are a developer, you should get feedback from other developers who are solving the same problem, and they work in the same company, and they maybe sit on the other side of the cube wall, right? Stand up and talk to people. But most importantly, find the path that works for you. We found the path that worked for us. You don't necessarily have to do what we did. But if you get started and iterate, you'll find that path, and you'll find it very quickly. So, none of this could have happened without the excellent work of our software development teams, our systems engineering teams. We love these guys. We want more of them, so we are hiring. You can find all of our job listings on careers.move.com/jobs. search for technology. It'll bring up all the jobs that are in all the locations that we have, and it changes frequently. I appreciate you guys taking the time to listen to me today. I've enjoyed it. Thank you very much. I'm going to hand it back to Nathan.
I got caught up there for a second. So I just want to say thank you, everyone, for attending. We have a lot of exciting announcements coming out on ECS. Not only does reInvent, but we're continuing to develop this product and make it better for everyone. So I encourage you to keep in touch with the team. Make sure that you follow the AWS Tech blog for news about ECS. And if you're interested in getting started with ECS, I highly recommend looking up on GitHub. We have a repository called Awesome ECS that has a list of resources that are created by the community and for the community by many different companies that are using ECS. And what they've actually done is open sourced tooling, example architectures about how they actually operate containers within ECS. And so you can use that as a starting point or just something to learn from the code if you're a hands-on learner. So thanks a lot for coming today.